All right, today we're going to crack open a really cool engineering mystery. How in the world did modern diesel engines go from being these loud, clattering machines to the seriously quiet powerhouses we have today? Well, the answer is a tiny little secret that, believe me, changed absolutely everything.
You know, if you've ever stood next to an older diesel truck, you know exactly the sound I'm talking about. That unmistakable kind of agricultural clatter and knock. But have you ever stopped to think, why was it so loud to begin with?
Yeah, it's not just something we imagine. That sound is a core part of the old-school diesel's personality. But as it turns out, that noise was really just a symptom of a super violent event happening over and over again inside the engine cylinders. So let's dive into what was really going on.
Okay, so to really get the solution, we first have to understand the problem. And it all boils down to how early diesels delivered their fuel, basically with one single massive explosion for every single power stroke.
Think about it like this. The engine would just dump all the fuel for that cycle into the cylinder all at once. This fuel would mix with the hot, compressed air, and then, boom, a totally uncontrolled explosive ignition. That violent spike in pressure is exactly what you hear as that classic diesel knock. Now, this whole single Big Bang approach didn't just create a ton of noise. It also put engineers in a really tough spot when it came to pollution. It locked them into what seemed like a completely impossible trade-off.
And this right here, this was the great diesel puzzle. You've got two main bad guys in the exhaust: nitrogen oxides, or NOx, which cause smog, and particulate matter, which is basically that fine black soot. The problem was, anytime you tried to reduce one of them, the other one would get worse. It was a total catch-22.
This put engineers in such a bind. I mean, if they cranked up the combustion temperature to burn off all the soot, that intense heat would create a whole bunch of NOx. But if they lowered the temperature to cut down on the NOx, they'd end up with these clouds of black, sooty smoke. For decades, it really seemed like there was just no way to win. But then, researchers started playing around with a deceptively simple idea. It was a concept that had actually been kicked around since the 1930s. But now, they were looking at it again with fresh eyes and modern tech. Instead of one giant, violent explosion, what if you could actually manage the combustion process? What if you could introduce the fuel a little more gently, in stages, and sort of tame that explosion into a smooth, powerful push? And this, right here, this is the secret: pilot injection. It's a tiny little preliminary squirt of fuel, we're talking just 5 to 10% of the total amount, that goes into the cylinder just moments before the main dose. It's kind of like a warm-up act for the main event. So here's how it works. First, that small pilot shot gets in there and starts a small, gentle combustion. Then, there's a very precisely timed pause. They call it a dwell. Finally, the main injection of fuel enters a cylinder that's already burning and perfectly ready for it. And the effect of this one tiny change? It was absolutely revolutionary. I mean, it fundamentally altered the physics of what was happening inside that cylinder. This is seriously the perfect way to think about it. The old way was like dousing a log in gasoline and tossing it on a fire. You get that sudden, violent whoosh. Pilot injection is like carefully lighting some kindling first. The big log catches fire smoothly and burns powerfully, but without that explosive shock.
So what's happening on a technical level is that this pilot shot basically preps the cylinder. It shortens the time it takes for the main fuel to ignite, which lowers the peak heat release, and it dampens that explosive pressure spike. That is the magic that silences the knock.
And the result was just staggering. Research back in the mid-90s showed that a tiny little pilot injection could slash combustion noise by as much as 10 decibels. Now, to our ears, that's a massive, massive difference. It completely transformed the entire character of the engine.
But the story doesn't stop there with just noise reduction. See, once engineers had this incredible new tool, this ability to inject fuel multiple times in one cycle, they realized they could use it to finally solve that impossible emissions trade-off.
So they started experimenting with adding a third small squirt of fuel. But this time, it was after the main power event was already over. This injection wasn't about making power at all. Nope, this one was all about cleanup. This is called post-injection. It's a precisely timed shot of fuel whose only job is to manage the chemistry of the exhaust gases that are still hanging out in the cylinder.
By injecting this extra little bit of fuel into the hot, expanding gases, engineers could literally burn off leftover soot particles after the main combustion. This meant they could tune the main event for lower NOx and then use this post-injection as a separate cleanup phase for the soot. They finally broke the NOx-PM trade-off.
So when you step back and look at the evolution of the diesel engine, you see this really clear journey away from just brute force and towards incredible, microscopic precision. Back in the early 90s, you had these mechanical pumps forcing fuel in at maybe 300 bar, which is around 4,400 psi. Fast forward to today, and electronic common rail systems can fire off 5 or more precise pulses per cycle at pressures hitting an incredible 2,500 bar. That's over 36,000 psi.
And that's the real secret, right there. The quiet, clean, and efficient diesel engine of today wasn't born from some quest for more raw power. It was born from the quest for microscopic, millisecond-level control over the combustion event itself.
This technology just shows us how a problem that seemed fundamentally unsolvable for decades was cracked open not by using a bigger hammer, but by using a more precise scalpel. And it really makes you wonder, with this level of control now at our fingertips, what other impossible engineering challenges are we going to solve next?